Good evening, everyone. Welcome to TPIsoftware's May webinar. My name's Peggy, and I'll be the host of this event. As a new wave of data analytics, more and more businesses, including corporate giants like Google, LinkedIn, PayPal, and eBay, all leverage graph data science to unlock the potential of data connections. Graph databases are also widely adopted in the financial sector to tap into data relationships, and Neo4j is one of the most popular graph databases, which is highly scalable. So today our webinar will talk about graph data science and how Neo4j provides insights into fraud detection. Let me introduce our two speakers today. For the first part of today's webinar, we're delighted to have our first speaker, Robin. Robin is the General Manager for Neo4j Greater China Region. He's an established thought leader in big data analytics and featured as regular speaker in industry and IT events. Today, he's going to give us a brief introduction to graph technology and talk about fraud and AML SOLUTION. We also have BNC Technology with us today. BNC Technology is Neo4j's reselling partner in Taiwan. John, General Manager of BNC, is here to support us in the event. Our second speaker is Tang-Wei. Tang-Wei is our data analyst and specialist, and he has extensive experience in Neo4j and data analytics projects. In part 2, Tang-Wei will further look into graph data science in Neo4j, followed by the use of Neo4j in financial fraud detection with a demo. At the end of this webinar, we'll have a Q&A session, so please feel free to send your questions anytime by using the chat box on your right-hand corner of your screen. Now, let's welcome our first speaker, Robin.
Thank you very much for the kind introduction. So I'm Robin. I'm from Neo4j. I'm the General Manager for Greater China. So today what I would like to really introduce to you is this whole concept of a graph data platform. But I would like to start with this whole concept on how context is very important in decision making. Now, in any organization that you are in, you are making a lot of decision on your data. You're running a lot of analysis, a lot of machine learning, and even AI to really understand more about your business. And really to have a good analysis or machine learning, you really need to understand the data in the form of connections and the context so that you can make very practical and actionable decisions. So for you to have context, it requires your organizations to progress from just collecting a lot of data to start connecting all this data together. So if you look at a lot of the data journeys that enterprise are going through, they started with having data and trying to collect them in a central location like a data warehouse or a data lake. And the whole intent of that is to be able to provide some form of business intelligence for them to analyze, to be able to do some dashboard reporting. However, the next step is to really connect all this data that has been connected together, and that is to be able to solve deeper problems, to solve more complex use cases by looking at the connections and the relationships of the data. And to do that, you need a graph technology like Neo4j in order to run graph queries and graph algorithms for you to be able to look at the data and analyze the data in a different format. Now, so what do I mean by a graph database or a graph data platform? So over here, I would like to explain in a very simple term the difference between a traditional database and what is a graph database. Now, a traditional database is something that you will be very familiar with. In most of your organizations, you would have a relational database like Oracle, Microsoft SQL Server, VB2, etc. And in this case, data is actually represented in tables, many tables, in rows and columns. And that has been used by many organizations for many, many years. This is a very established and mature technology, and it serves its purpose well and does what it does very well. However, a traditional relational database is really not designed for you to do very complex types of link analysis or to be able to look at relationships that are very, very deep. And the reason is that relational databases has certain limitations when it comes to the number of queries that you can do or the number of complex relationships that you can start to join, because you will hit a lot of performance issues and you'll hit a lot of rigidity issues. Now, on the other hand, what you see on the right-hand side is a graph database. It is Neo4j. And over here, you realize that the data is represented very differently. You cannot see any tables, you cannot see any rows or columns. But what you find here are what you can see over here are circles and arrows, circles and links, or what we call nodes and relationships. Basically, you can see that how the data is being connected together, and the connection can go very deep, from 1 degree of connection to 2 degrees to 3 degrees to 10 degrees to 100 degrees, and it can go as deep as you want to. And that will actually help you enable new types of use cases that cannot be done easily on the traditional database. And what do I mean by that? So if your use case, if what you're looking at will be links around people, how your people are related to one another, and when I talk about people, it will refer to employees, customers, suppliers, partners, influencers, and so on, or to be able to link transactions together, purchases, bank transactions, money flows, and so on, or even knowledge, like a supply chain knowledge or risk management and so on. And when you want to start linking and connecting all these things together, this is where graph technology like Neo4j will be able to help you to unlock that whole deeper context for you to be able to do a deeper analysis. So what are some of the types of use cases or business problems that Neo4j solve through graph technology? There are many over here, but I just want to list down some just to give you an idea. So the first one will be in areas to help you in better decisions. So for example, in fraud analysis, network analysis, and forecasting. Second one is on customer experience. How do you be able to predict customer journey? How do you do customer segmentation, customer 360? The third one will be around data unification. So in areas like data 360, data compliance, or how do you do things like data lineage, data governance, and so on, right? And you can use graph to help you to do better product recommendation, to be able to help you to do better personalization of your services and web pages, and many other things. So as you can see, the application, how you apply graph technology like Neo4j is very, very diverse. It can be many different areas. Now, of course, I understand that in today's session, Tang-Wei will actually walk you through in a lot more detail on the area of fraud using Neo4j, and I shall leave that into the next session. Now, so this is another slide that shows you a lot more details in terms of the common use cases for graph, especially in financial services, in banking, in insurance, in financial securities. So you can see that one of the key areas will be around risk, fraud detection, right, and anti-money laundering, even in data lineage, compliance, customer 360, and so on. So there are many different ways that you can apply Neo4j. Now, so who is Neo4j? Now, of course, all of us will realize the importance and the growth of graph technology. Now, Neo4j is the undisputed leader in this area. We have been in business since 2007, and we started this whole concept of graph technology. And you can see in leading analyst reports like Forrester or DB Engines, we have been at the top right-hand corner as the market leader. And the reason is because we have invested a lot of research and development to really come up with a product that is easy to use, that is scalable, and that is of good performance. But what is really more important than having a good product is that we have a very strong community. Now, Neo4j roots are open source, and because of that, the adoption of the technology is very wide. There are many people, many developers, many data practitioners that are using Neo4j. And this is important because as a company, as a data scientist, as a CIO, as a data engineer, whenever you want to make a decision on a technology, you want to make sure that this technology has been used by many different people, and that it has a very wide and strong community, and there are many people with that skill sets, because this will future-proof your investment. And these are just some of the customers that we have in financial services, and you can see this over the world. In Asia, in Singapore, we have customers like Standard Chartered Bank, DBS, and even in Taiwan, We have customers like Cathay Financial Holdings that are also using Neo4j. And of course, this is just a subset of the customers that we have in financial services. But financial services is definitely one of the key industries where Neo4j shines very well in. Now, so I will just touch very, very briefly on fraud and anti-money laundering because Tang-Wei will actually go into a lot more details. Now, so when it comes to fraud and anti-money laundering scenarios, there are many, but I just want to go into a few details. So one is on ownership structure, right? How companies are being structured. Are there shell companies whereby the directors of the companies are actually doing a lot of layering, a lot of shell companies to actually hide their money, right? So that is one area. And then you can also look at money movement. How do you concentrate you do a lot of transactions within a certain threshold so that it will bypass a lot of this fraud detection rules or anti-money laundering rules, right? So there and how do you do rapid movement money or flow doing money flows whereby you transfer the money from many different people, many different layers, and then eventually the money coming back to you. So these are very common AML scenarios or fraud scenarios. And this will be actually easily solved and very effectively solved by graph technology like Neo4j. So over here, I will not go into the details, but what you can see is that from the left, you will have a lot of the data about the networks of people, transactions, your customers, and so on. So you have all this data, you will start to ingest it into Neo4j, and it will create what we call a fraud model, fraud and AML model. And there you can start to do your investigation. You can start to run some of this machine learning prediction, and the graph will actually help you to come up with different clusters, different categories, different scores or segments of or transactions of people, whereby you can focus your investigation in, right? And leveraging the power of connected data. Right. So with that, I actually will end my sharing. I'm given 10 minutes. And what I hope to do in this sharing session is to give you an idea of the potential of graph, how you can use graph. And of course, today we will focus a lot on fraud and anti-money laundering, but we can actually apply this to many different areas. With that, I shall pass this to Tang-Wei, who can actually lead you into a more detailed discussion. So that's all that I have. I just want to thank you very much and have a great evening ahead. Thank you.
Thank you very much, Robin, for your introduction to Neo4j and the AML solution. Now I'm going to hand over to our next speaker, Tang-Wei, who's going to continue the topic about graph data science and how to leverage Neo4j in financial fraud detection with a demo. Let's welcome Tang-Wei.
Hi, and thanks for Robin and Peggy. And this is Tang-Wei Hong, and I am a Neo4j specialist and at TPIsoftware. So I'd like to thank everyone for coming in today. And this is a really important topic, and I'm very excited to talk about it. So today I would like to introduce the topic about graph data science with Neo4j to detect financial fraud with a demo. So let's get started. So after we have some basic knowledge of graph data from Robin, I think we can move to the part of graph data science. So we all know data science is answering questions using data. What's graph data science? And in Neo4j, we like to say relationship is our key factor. At graph data science, it's basically using those relationships between your data point to answer questions. Instead of just saying, here are my rows and columns, I wanna predict this outcome. We look at those connections between those rows and columns between your data point and use those connections to those relationships to answer questions. So you start having these multi-hop relationships, and we talk about graph data science, and it's really a combination of graph queries. So that core database functionality, and I have stored all this data. I wanna answer questions about how it connected. And we talk about the graph algorithms, which are unsupervised machine learning techniques, and let you find patterns in your data, understand the topology and what's important in your graph. And then let visualization tools, so everything from brooms to our tabular integrations, seeing and interacting with the data relationship first to understand how relationship influence outcomes. So when we talk about graph data science, I think it can sound a little terrifying. So, okay, we are gonna run graph algorithm, but I'm not familiar with the network science. So how do I get started? Well, I like to think of it like a process. So here are different phases of graph data science, the iterations of the graph data science. So in the step one, I need a knowledge graph, right? So to do the graph data science, I need to have some data in a graph. And I can do that local pattern matchings. I can answer questions, matching these patterns, and find me all compounds that are connected. And that's really for decision support. And building on that, so I have a graph, then I can start doing graph analytics. And what that means is running graph algorithms or running global queries to answer specific questions. So I want to know how many disjointed subgraphs do I have, how many communities are there in my graph, and I'm gonna just run weakly connected components, and I can gonna take the result of weakly connected components, and I am gonna head that off to an analytic, and that's gonna be used to make a decisions. So I'm running this global algorithm to understand the structure and topology in my graph, but it's still to answer equations. So in step 3, building on that, getting a little bit more complicated, we talk about graph feature engineering. And here you are using the graph algorithms, but instead of running 1 or 2 or 3 algorithms in succession and handing it off to a human to review, what you are doing is you are using those as features that are inputs for a model. So I'm gonna build a predictive model. I'm gonna use an algorithm to generate graph-based feature to summarize the topology of my graph. So I can get it into my machine learning pipeline. So this is the step 3. And the 4th step, we talk about the graph embeddings, and which are basically a specific category of algorithm. And instead of PageRank, it's always the same. The graph embedding is how you calculate it. You basically learn what's important about your graph and your use case. And you can customer calculate a graph feature or a feature vector that describe every node in your graph in the topology. And these are really the input for the graph native learning or graph neural network. So this is the iterations of the graph data science. Now, after talking about the iterations of the graph data science, we could see here have a lot of applications that graph data science can apply, such as the fraud detection or life science. So what does the Neo4j do for the graph data science? So when we talk about the Neo4j for graph data science, at the heart of the ecosystem is the graph database, right? That hosts your graph data in a graph shape. And it's a native graph and it's persistent. So you can query it, you can update it, but let's integrate it into a bigger ecosystem of other tools. We have the graph data science library that lets you run the scalable graph algorithm and graph embedding, and it lets you do analytics at scales. So it lets you reshape your graph, running super efficient data science pipeline, and answer questions about the data that you have. So Neo4j also have the tools like the brooms that really lets you do is when you download data science, how do I communicate that to my partner? How do I share it? So you can use the broom to explore your data to your partners. And the GDS library is a plugin of the Neo4j. So you need to install Neo4j, and then you can install the graph data science library. And there's really two parts to the GDS library. So we talk about the graph algorithm. That's kind of what people think of when they think of the graph data science. So I want to do the community detection. I want to do the centrality. I want to do link predictions. So what the graph data science library lets you do is you can run this algorithm at scale. So you run against a load graph, and you can scale into tens of billions of nodes. So this really lets you answer questions about interconnected data at scales. Now the other piece is the analytic workspace, or the in-memory graph. And this is kind of like a secret source of the GDS library. So you have your database. I think it's like a kitchen sink. But when you're doing the data science, you don't necessarily need all of the data, and sometimes you need it in a different shape than it's in your database. So we have the graph loader and the in-memory graph to let you slice, subdivide, recombine, aggregate, reshape that graph into a graph structures. And you can combine this in-memory graph for workflows and layering algorithm. And that's what I'm gonna show you in the demo later. But taken together, there are kind of the two main pieces of the GDS library and how we let users do the graph data science in the Neo4j. And here are some simple queries to advance machine learning. So we can have the query, and we can have the algorithm, and we can have the embeddings, and we can have this output as our features to our machine learning workflow. So we can train the ML model based on the result, the query, algorithm, or embeddings. And here are some Neo4j graph data GDS library provide the graph algorithm like the path finding or community detection or similarity. So here are some details about the GDS library, the graph algorithm in the GDS library. Like in the graph embedding, Neo4j provide the not-to-vec or phase RP, or in the community detection, Neo4j provide the triangle count or the vein. So this is all the graph algorithm in the Neo4j GDS library. Okay, so let's get into today's visuals. So how to use the graph for the fraud detections. Okay, so when we talk about the fraud detection in graph, I think we need to have a little concept of fraud rings. So if we look at what a fraud ring might actually look like in terms of modeling, if you have a few different account, each of those accounts have some attributes. So if I look at account holder 1, we know that they have a credit card, we know they have a bank account, we know they have an unsecured loan. And account holder 2, we can see that they have a social security number, another credit card, another bank account. All of these things look normal in and of themselves. And it's only when you can make additional connection between them where you can see the account holder 1 and account holder 3 share the social security number, and which really shouldn't be happening. You can have two people have the same social security number in the US. You can start seeing patterns of shared information that will raise red flag, and that will give a cause of concern, and many indicate that you are seeing a fraud ring. So how can we act on that? How can we fight this fraud ring using the graph? And so we are starting with a quote from the Gartner. So let's say in the market guide for the online fraud detection in the 2015, it said, I don't consider traditional technology suitable to keep up with criminal trends. What they mean is that have got this 5-layer model for the fraud preventions. So the first 3 elements of that models are traditional fraud detection method, and is what we mentioned before in terms of event-based transactional type fraud detections. So like the endpoint centric to identify user by the device they use, the PCs and the mobile phone and looking for the odd behavior for those accounts among their endpoints. And the second layer is navigation-centric. So analyze of navigational behavior and suspect patterns. So look at IP address, the user IDs, the step that those user IDs take, and what a typical path would be for navigation for that type of users. And the number 3 is account centric. So analysis of money and behavior for user accounts or within a channel. And these are quite traditional. They won't go away and they have stopped certain type of fraud. But the fraudsters have had to evolve, have had to move past this. So they know this is what's happening now and they need more smart way of performing fraud. And what are these traditional methods are largely unable to do is identify the fraud rings or to deal with fake IP address or deal with hijacked device or identify the synthetic and stolen identities. So this is a visual of that. You have got a range of normal behavior and traditional you will investigate these outliers. These things that look out because they are so far outside the normal patterns of behavior. However, modern fraudsters hide their fraudulent behavior amongst normal behavior. And if you looking for the outliers, you won't find it in this sort of scenario. But you really need to be able to find patterns that represent the fraudulent behavior hidden amongst what were otherwise be considered your normal behavior patterns. So therefore, this is where layer 4 and 5 come in. So layer 4 in the Gartner model is cross-channel and less correlating and behavior across channels. And the number 5 is entity linking. So looking for the relationship that might allow you to detect organized crime or ring of fraudsters and collusions amongst different entities or different actors as part of fraud. So this is where graph database can really add values. So graph database address Gartner's 4th and 5th layers of fraud preventions, the cross-channel and entity link analysis. And the graph database enables banks to look beyond the individual data points of discrete analysis to the connections that link them. So with graph database, banks can see their data in graph and more easily visualize patterns and the opportunity to better predict when and where the fraud might occur. So, okay, after we introduce the brief concept of using graph for fraud detections, we will take a look at the data that we are going to be using in our demo. So when we talk about the banking and looking at the graph for banking or data for banking, a bank can have a lot of different types of informations. You can have internal information, organization information. You can have information about your customers, about your products, or even data, payments, or money transfers, or even the third-party data like the social media or credit rating agency data. But today, we are really gonna be focusing just on 2 or 3 areas. We are really gonna be looking at customer data and specific a bit of identifications you might have about a customer, such as a bank and event data, so like the movement of money, the transaction between the accounts. So in this demo, I will use the pacing as dataset, which provided from Neo4j. So to understand pacing, we need to understand a little about what it was built to the model, specific a model money network. So the mobile money takes different forms, but in the case of pacing, it involves both bank and participating merchants. So the merchant can take mobile payments via the network, so for a good or service, as well as perform the functions of putting money into the network, like the topping up an account. So if it sounds a little like the Apple Pay, it's because mobile payment services are effectively a type of mobile money. So consider it something like the Apple Pay, but where you can also make deposit via the participating merchants. So in paysim dataset, here are two main components, the agents and transactions. The agents can perform actions in this dataset. So here are three types of agent in paysim. The first one is clients. So the clients are the end users in the mobile money network. The clients maybe is faster, most or normal customers. Now the second one is merchants. So merchants are the vendors that participate in the network through the interaction with clients. The final one is banks. So banks is this dataset only act as targets for the debit transactions. So here goes another important component in paysim, the transactions. In paysim dataset, transactions are the only real way that clients can interact with other agents. So here are 5 possible transactions: the cash in, cash out, the debit, the transfer, and the payments. So here is our data model look like before we dig into the actual demo. So in here we can see we have the clients and we have the transactions, and the clients has the email, and the clients has the phone number, and the clients has the SSN numbers. And the client can perform the transaction to the merchant, or the client can perform the transaction to bank, or the client can perform the transaction to another client. So this is our final data model look like in our paysim dataset. Okay, so what are we doing after we have dataset? Well, here are 5 steps to perform financial fraud detection in this demo. The first step is framing the problems, which financial problem we need to solve. The second step is EDA, the data explorations, to explore our dataset. The third step is detect the first-party fraud. And the fourth step is detect second-level fraud. And the final step is using machine learning technology to detect fraudsters. So in the previous slide, we want to detect first-party fraud. So how should we do? Well, here are some main concepts in the first-party fraud detection. The first, we need to identify the cluster of clients who sharing personality informationable information. So we call the PII, such as sharing the same SSN number, or share the same phone number or address. Second, we need to calculate the pairwise similarity on the clients who sharing the PII. And finally, we will compute a first-party fraud score to label the potential first-party fraudsters. So in the second-party fraud detection, we will perform these 3 main steps. The first is to identify the clients who interact with first-party fraudsters. And next, we will explore the type of transaction between those 2 groups. And finally, we will use some graph algorithm to compute the second-party fraud score. Okay, so before we demo, I think here are some points we can mention first. So what graph algorithm we will use in this case? So in current, the large financial companies already apply some graph algorithm to detect fraud. So for fraud, we tend to use connected component algorithms. So it's a type of community detections to identifying how are groups of individuals related or connected. So in that first-party fraud example, weakly connected component is typical one that people reach for to find who are people that are sharing those common identifier, or called PII. And next, PageRank, which we'll be using today, is commonly used centrality algorithm for scoring how important or influential a particular person is. So this is the algorithm that come out of Google years back. So Robin is a type of community detections. We will be using a different type of community detection, but it's fairly commonly used. And finally, J-card is a great way for calculate similarity between accounts. So if you're thinking of using graph data science and you have got a fraud detection use case, these 4 graph algorithms you could start looking at the first. So to be more detailed, so the PageRank is to find important nodes based on their relationship. So therefore, we could identify important and information kindness nodes by the quantify the flows of money toward them. Okay, so here we can see the PageRank algorithms in our pacing data set. So we can see what nodes can be considered important in our graph based on the money flows. So in this pacing data set, the inputs and the outputs of the PageRank algorithms. And the weakly connected components is to identify community based on the connection with shared piece of identities. So here is the weakly connected components algorithm in the pacing dataset, and we will use and the input and outputs. Okay, so same as the node similarity to identify the similar node who share a common piece of identities. So same as previous, so we can see the input in our the input of node similarity algorithm in our pacing dataset. Okay, so the final is Robin community detections. So to useful for identify the community based on the transaction behavior rather than identities. So the Robin algorithm in our pacing dataset. So what community of nodes transact amongst themselves, and this is the input and the output of our Robin algorithm in our pacing. Okay, so let's get to our demo part. So let me, okay, so let me transact to the Neo4j. So, okay, let me check. Okay, so this is our Neo4j database. So we can see here are some nodes like the kindness, the phone number, and the first step we will do in the demo is the EDA. So the first in the EDA, we will show the database schema. So in here, we can see this is our pacing database schema. So in here, we can see we have the kindness, and the kindness have the phone and has the SSN number, and that has the email. And then here are another. Okay, so here is another like the transaction to the bank or to the merchants. So this is our database schema. Okay, so the next step, we will do the node label statistic. So we will integrate the database to get all node labels like the kindness, the transaction, or something, and we will run a subquery using the APOC to get the label counts. And then we will analysis the label counts against the global label counts. So in here, we can see the result. So most of our transaction activity is some form of ingress or egress, where money flows into or out to the networks, while the transactions, the remaining of activity involves money flows to and from parties in the networks. So this is our node label statistic. And then we will do the transaction type statistic. So here are 5 types of transaction in this database. So list all transaction type and corresponding metrics like total market values, relative market values, or number of transactions by iterating over all the transaction of all transaction types. So we can see the cash-in transactions still dominate in terms of quantities and average transaction size. But interesting transfer transactions make up over 1/3 of the total market activity in terms the amounts of money involved, even so they are hardly 6% of the total transaction volumes. So in fact, the average transfer involves found 6.25 times the average cash-in transactions. So what does this mean? The money is passed around in large quantities more than is injected into or removed from the network. So given that fact, we will probably see something interesting when we look at the transfer of money between clients. Okay, so this is the part of the EDS. So we can see some data exploration in our pacing data set. Okay, so the next part we were to do to detect the first party fraud. So in here we will perform the 5 steps. The first is to identify clients sharing personal identifiable information, the PII. And then we will identify a cluster of clients sharing PII using community detection algorithms. And then we were finding similar clients within the cluster based on shared identifier using pairwise similarity algorithm. And then we were calculating and assign the fraud score to clients in cluster using similarity algorithm. And finally, we will use using assigned fraud score to label the clients as potential fraudsters. Okay, so here in the first step, we can identify the clients who sharing the PII. So in here, we can see here is one client and here is another client. So we can see these clients share the same phone number with this client. So we mark all these relationships together. And then we were creating a new relationship. So we will create a new relationship to connect clients that share identifiers and add the number of shared identifier as a property on the relationship. So what it means, we can visualize the result. So we take this clients as a sample. So this clients share 3 PII with this clients. So they maybe share the same as a number, share the same email, or share same phone numbers. So we can visualize the new relationship. And then the next step, we will identify the cluster of clients sharing PII. So identifying cluster of clients sharing PII is by running one of the community detection algorithm in our GDS library. So we will use the weakly connected component to find a group of connected nodes, where all nodes in the same set from connected components. So WCC is often used earlier in an analysis to understand the structure of the graph. So here we will load our graph into the memory using the native projections. So we choose WCC as our graph name in this tutorial for running WCC algorithm. Okay, and then we will write the result to the database. Okay, and then we can visualize the result and collect clusters. Okay, so in here we can see here are some clusters. So it may be the cluster 1 and maybe the cluster 2 based on the WCC graph algorithms. Okay, so the next step, we will create a graph for the similarity. So to finding similar client with a cluster is by running one of the pairwise similarity algorithm in our GDS libraries. So we use the node similarity to find similar nodes based on the relationship to other nodes. So the node similarity use the J-card matrix, which computes similarity score for a pair of nodes by looking at related nodes in the network that are common to both the nodes divided by the sum of all nodes related to both of the nodes. So in here, we will create the graph for similarity algorithm, and then we call this graph name as similarity. And then we will write similarity to the in-memory graph and to our database. So we write the result to our database, and then we can visualize what we do in the similarity step. So in here, we can see we take these 4 people as an example. So this is the kinase 1. So we can see this kinase and this kinase share the one PII, same PII. And then we calculate the similarity score, we can see is 0.2. So this the similarity score is 0.2, or here the same, the J-card score. Okay. And then we will do the first party fraud scores. So in this step, we will compute and assign fraud score, the first party fraud score, to the kinase in the cluster identified in the previous step based on the similar to relationship weighted by the J-card score. So we can see that in previous step, we can see maybe one J-card score is 0.2. So we use one of the centrality algorithm, the degree centrality, to add the J-card score on the incoming and outcoming relationship for a given node. And these scores represent clients who are similarity to many others in the cluster in terms of sharing identifiers. So here are here's the assumption is higher the first party fraud scores greater the potentials for community the fraud. So we can see we write the degree centrality to the database, and then we were adding the label to the client based on the fraud score. So if this score is higher than the threshold, we will label this client as the potential first-party fraudsters. So we can see we label the 75 kinase as our first-party fraudsters. Okay, so this is part of how to detect the first-party fraudsters. Okay, so the next part, we will do the second-party fraud, second-level fraud detections. So in here, we will identify and explore the transaction between the first-party fraudster and other clients. And then we will identify second-party fraud networks. So in the first step, okay, we can see in the first step is to find the clients who are not identified as first-party fraudsters, but they are transact with first-party fraudsters. So maybe we can see these persons. Okay, so we can see these clients as examples. This is the first-party fraudsters we label in the first-party fraud detections. And then this person is not labeled as the first-party potential fraudsters, but it has the transact with these persons. So we identify this transaction with first-party fraudsters and clients. Okay, and then let's find out what types of transaction does this client perform with first-party fraudsters. So we can see all these transaction type is the transfers. Yeah. Okay, so the next step, we will create a new relationship. So let's go ahead and create the transfer to relationship between the clients with first-party fraudster tag and clients with no such tags but transact with fraudsters. So let's go ahead and add the total amount from all such transaction as a property on transfer to relationship. So we create the transfer relationship between the clients with the first party frusters. So we can visualize the relationship. So in here we can see we create the transfer to relationship. So this people is labeled as first-party fraudsters, potential first-party fraudsters in previous step, and then this client is not the first-party fraudster, but this client has transacted with this client. So we made the transfer to relationship and then label as the second-party fraudster suspect. So okay, so the next step, we were identifying the second party fraud. So our goal is to find out the client who may have colluded with first party fraudster and were not identified as potential first party fraudsters. So our hypothesis is that clients who perform the transactions of type transfers, where they either send to or receive money from first-party fraudsters, are suspects for second-party fraud. So to identify such clients, make use of transfer relationship and use these recipes. The first is use the community detection algorithm, the WCC, to identify network of clients who are connected to first-party fraudsters. And then we will use a centrality algorithm, the PageRank, to compute a score based on how influential these clients are when relationship take into account the amount of money transferred to or from the fraudsters. And then we will use the PageRank score to assign the second-party fraud score, like the risk score, to these clients. So the first step, we will execute the WCC to find the clusters. So we will see if there are any cluster with more than one client in length, and if there are, then we should add a tag, the second party fraud group, to find them later using the local queries. So here we create a memory graph, and then we execute the WCC algorithm. Okay, so the next step, we will identify the second party fraudsters. So let's go ahead and compute the centrality score using the PageRank algorithm to find out who among the suspects have relatively higher PageRank scores. So you can see we identify the second party fraudsters by using the PageRank graph algorithm, and then we will get the PageRank scores. And then if this score is higher, we will label this client as the second level fraudsters. So we can visualize our second party fraud network. So here are our second party fraud network. We can see here are some network in our pacing dataset. Okay, so let me clean the memory graph, and then to perform our final step, to use the machine learning technology to identify the fraudsters. So okay, so let me boom some first. Okay, so in this machine learning step, so in this machine learning step for fraud detection, we were using some machine learning technology to detect the possible fraudsters. So here are 8 steps we will perform in this demo. The first, we will label the suspect fraudsters, and then we will use the Levin algorithm to cluster the clients, and then we will label the innocents, and then we will calculate some other properties, and the 5 step is to perform some feature engineering. And then we will run the FaceRP algorithm and then run the Neo4j algorithm, which these two are the graph embedding algorithm in Neo4j. And then we will train the model and get the result. So in the first step, we will label the suspected clusters. So we all know the node classification is a supervised machine learning approach whereby it states nodes with known classes can be used to train a model that will learn the class of node for the node. So where are they unknown? So in order to achieve this, the data must be split in two parts, a training graph and a testing graph to predicting the classes of unknown nodes. However, in this pacing dataset, it doesn't have the label data. So therefore, we need to create some label data that present the suspect clusters and innocence in this dataset. Okay. So in this case, if the kinase perform the number of fraud transactions more than 10, and it will be the suspected fraudsters. Also, if the kinase are the first-party fraudsters or second-party fraudster that we have done in previous, also be labeled as suspected fraudsters. So in here, we will label the suspected fraudsters. And then we will use the Robin algorithm to cluster the kinase. So we can use the Robin algorithm, which are useful for identify community based on the transaction behavior to find communities in our graph who are connected. So we load the in-memory graph, and then we save the Robin result into our graph database. And then the next step, we will label the innocence. So it's time to label our innocence kinase in this database. So in this case, the way we label innocent is if the ratio of suspected fraudsters in the Robin community less than 0.065, then we will label this kinase is innocence. It means this kinase has a very little possible to become a suspected fraudsters. Okay, so the next step, we will calculate some other properties. So in this step, we will calculate some other properties in our pacing dataset, such as the degree or page rank or a triangle count as our other properties for our machine learning pipelines. And then the next, we will perform some feature engineering. So we will use Cypher to do some feature engineering, such as count the number of fraud transactions in this pacing dataset of this kinase. Okay, and the next two parts, we will run the FaceRP and Neo4j graph embedding algorithms. So the FaceRP, the phase random projections, is a node embedding algorithm in the family of random projection algorithm, which one can project vectors of dimension into all dimensions and still preserve pairwise distance among the points. So we will use the FaceRP algorithm to perform the node embeddings. And then we will perform another node embedding algorithm called the Neo4j. So Neo4j is a node embedding algorithm that computes a vector's representations of a node based on random walk in the graph. So we will use the Neo4j algorithm to perform another ways for our node embeddings. In here, we the first step, we need to have the label data. So we need to label the suspected fraudsters, and then we need to label the innocence kinase in our database. This is because we will do the node classifications, and node classification is a supervised machine learning approach which we need the label data. And then when we get the label data, we will also perform some feature engineering, or we can calculate some other properties to make more features. And then if more feature in our machine learning models, and it can have more accuracy for our models. So in here we were doing some feature engineering, like to calculate some other properties, or to use the cipher to do the feature engineering, such as account the number of fraud transactions. Also, we will use the node embeddings algorithms in our pacing dataset, and we will use the face RP algorithm, and we use the node-to-vet algorithm in our feature engineering part. Okay, so when we all have these components, we can put these results to our machine learning models. So in here, we will load a graph to make a predictions. So in the first step, we can see we split our graph in two parts. One part is our training part, and another part is the testing part. And then we set the label data as 0 and 1. The 0 is the suspected fraudsters, and the 1 the 0 is innocent kindness, and the 1 is suspected fraudsters. So in here, we load a graph to make predictions. Okay, so the next part, we will train and pick the best models for our machine learning models. So in here, we can see here is the winning models, and here are some parameters in this model, like the max apex, the penalty, or the batch size, or the tolerance. And here we can see these winning models. In our training graph, the accuracy score is 0.87, and in our test graph score, the accuracy score is 0.85. So if we, I think this is little good result for our models. But if you can put some you can tune some hyperparameters to make this accuracy higher. So in here, we will train and pick the best models for our machine learning models. And then the final part, we can make the predictions. So in this part, we can boom here, and then it will use the winning models as our machine learning models to predict on our unlabeled data. So here we can see we can make the predictions. So we can label the data we want to make prediction on. So this is the cipher in the Neo4j we can use to perform the graph data science. Okay, so this part is to make the prediction, and then we can check out the result. So okay, so here is our result. So we can take one kindness as an example. So we can see in this kindness, we have the embedding feature in this kindness, also the loving community, or the degree, or we use the node-to-vet embedding, and then the page rank. And then in here, we can see this is our prediction models give the score. And this is predict fraud possibility, and we label this kindness as the possible fraudsters. Okay, so I think this is the part of demo And in this demo, we detect the first party fraudster, and then we detect the second level fraudsters. Also, we will use the machine learning approach, like to doing some label data, or to doing some feature engineering, or to doing some node embeddings like FaceRP or Node2Web as our features, as our feature inputs to our final machine learning models. And then we create this machine learning model in the Neo4j, and then to train and pick the best model, and then we will make the predictions. So this is today's demo part. So thank you for your attention. Now I'm hand over to my colleague Peggy, and I'm very happy to answer any questions you might have.
Thank you very much, Tang-Wei, for this amazing presentation. I hope you all enjoyed this presentation and have learned more about how we can fight fraudsters using Neo4j and graph data science. Now we're going to have a Q&A session to answer some questions we collected from the registration forms. Please stay tuned till the end of the webinar. I'll read out the questions on behalf of our attendees, and our speaker Tang-Wei will answer them. So the first question is, could you tell us when to use query, graph algorithm, or graph embedding?
Oh, okay. So thank you for your question. I think this is a very good question. Well, I think here are some easy ways to differentiate what situations we can use query or graph algorithm or graph embeddings. So the intent of query is real-time local matchings for some specific questions. So therefore, if you know the exact patterns you are looking for, you can use the queries. And another way, the intent of graph algorithm is to find the global patterns and trends for analytics. So I think if you know the kind of patterns you are looking for, you can use the graph algorithm. And the graph algorithm is like the centrality or WCC algorithm, or the similarity algorithm like J-score we use in our demos. I think if you know the kind of pattern you are looking for, you can use the graph algorithm. And finally, the intent of graph embedding is to create the highly predictive numeric presentations for the machine learnings. So therefore, if you know there's something important in your graph, but you don't know exactly what to look for, you can use the graph embeddings. So the graph embeddings is like we use in the demo, like the node embeddings, or like the graph embedding. And node embedding is like the FaceRP or Node2Web graph algorithm. So I think if you know there's something important in your graph, but you don't know exactly what to look for, I think you can use the graph embeddings. So does that answer your questions?
Thank you, Tang-Wei. Okay, let's move on to the next one. Can we tune hyperparameters or change the machine learning algorithm in the node classification?
And I think that's a great question. So thank you for asking. So please give me a moment to think about these questions. Okay. So let me see if I can clarify these questions for you. So I think you means in the machine learning, we can tune in the hyperparameters in all the machine learning algorithms, like in SVM or in the random street. So I think in the Neo4j graph data science, both node classifications and link predictions have training parameters that can be tuned automatically given a set of low values. So you can see in the demo, we don't have tuning the training parameters. We use Neo4j automatically to given our best parameters in our train and pick machine learning models. So I think if you want to tune in the hyperparameters, the parameters, and control how long the training will run until the terminations, you can set some values. So for example, we can change the number of max apex to maximum numbers of apex training until terminations, or we can change the batch size to affect the convergency rate in gradient descent in the training algorithms. So here are some more detailed information will be explained in the Neo4j GDS operation manual. So if you want to check which hyperparameter you can tune in the Neo4j, you can go to the Neo4j website and to see the optional manuals. So have I explained that clearly?
Okay, thank you, Tang-Wei. So our third question is, can we change the machine learning algorithm in the node classification?
Well, I think you have brought out interesting points. So let me think how I can clarify it for you. So I think you means in real world we have a lot of machine learning algorithm, like I said before, the neural network or the decision tree algorithms. And I think in the Neo4j graph data science, the node classification is based on the logistic regressions. So if you want to use other machine learning algorithms such as SVM or deep neural network I mentioned before, I think you can use the Python API to connect it your Neo4j database and then build the classification model by using the Python library, so such as the sklearn or PyTorch or Keras. And then when we get the result, we can write back the result into our Neo4j database. So I think in these situations, you don't want to use the logistic regressions, and then you want to use the SVM or random forest classifications models. You can you can use the Python API to connect your Neo4j database, and Neo4j also provide some library to help you to connect your data to the Python, and then you can build a classification model by using your familiar Python libraries like the sklearn or PyTorch. And then when we finish the classification model and make the prediction in the Python, we can save this result and then write back this result into our Neo4j database. So did I answer your question clearly?
Thank you, Tang-Wei. Okay, next question. How can we perform feature engineering in graph data science?
Okay, so thank you for asking that questions. So let me consider the best way to answer that. Well, I think in Neo4j, we could perform the connected feature extractions to improve the performance of machine learning models. So before we talk about the connected feature extractions, I think we need to know what is feature extractions. So the feature extraction is one of the sub problems of feature engineering. So it describes the process of how we change the shape or format of our raw data so that it can be used in machine learning pipelines. So the connected feature extractions in the graph data science is the process of changing the shape or format of graph data so that it is usable in machine learning pipelines. So the connected feature can be generated in two main ways. And the first way is the running local graph queries. So this works best when we know what we are trying to find. So for example, we can counting the number of fraudulent users up to the 3 degrees away from a person in a fraud graph. And the next way is we can running the global graph algorithms to get our connected features. So the running global graph algorithm and lists are used when we know the general structure that we want, but not the exact patterns. So for example, we can compute the PageRank score of all the users as an indicators of the potential fraudulent behaviors. So I think we can do some feature engineering in our graph data science, like to perform some connected feature extractions to changing the shape or format of graph data so that it is usable in a machine learning pipeline. Also, we can use some node embedding or graph embedding as our feature engineering. And it's like to running the global graph algorithm. So did I answer your question?
Okay, thank you, Tang-Wei. So one more question before we wrap up the session. Could you please briefly describe the workflow of ML in graph data science?
And I'm very glad you asked that. Well, in my opinion, I think we can separate the machine learning workflow into 5 parts in our graph data science. So the first part is we could use the query, the algorithm, or the embeddings to perform the graph native feature engineering. And the next part is we can train the predictive models. So we need to choose the model type, do the property selection, and then we can train and test our model, and then we can perform the model selections. And the third part is we could apply this model to extend our new data, or we could store model in database. And the fourth part is we could use the prediction for decisions or use prediction to enhance our graph. And the final part is that we could publish and share our model to the clients or to our partners or college. So I think these five part is the workflow of the machine learning in our graph data science. Yeah.
Hey, thank you, Tang-Wei. So this is the end of our Q&A session. That's all for today's webinar. Thank you, Tang-Wei, and thank you everyone for attending today's webinar. We've got a question asking about what TPIsoftware is, and here you go. We are TPIsoftware, a software solution provider delivering enterprise software and one-stop solutions to businesses in various industries. We also provide consulting services of Neo4j. Our speaker Tang-Wei comes from one of our solution divisions, which is AIoT Application Development Division. AIoT offers tools to create sustainable management and intelligent operation systems, including visual graphics engines, equipment automation control, advanced notification modules, project evaluation, intelligent control through graphical interfaces, and more. If you want to learn more about our Neo4j and AIoT solutions, feel free to contact us via email or a survey, and we will get in touch shortly. Before you leave, please scan this QR code or click the survey link we've just sent to the chat box to fill out the survey so that we can send you the slides and a link to today's video recording. We have lots of resources for you to explore, such as monthly newsletters that cover our event and blog articles on tech trends. Please scan to subscribe and follow us on our social media so you can stay updated for our latest news and future events. That's all for today's webinar. Don't forget to submit your survey before you leave. Once again, thank you everyone for participating. We hope to see you again next time. Bye.